Okay, now, I'm not gonna bring them over here, because they're kind of hooked up. We got the Helmholtz coils, okay? Bunch of wire loops here, a bunch of loops here, 10 centimeters apart, 10 centimeter diameter. Get a field at the center. Now, the field at the center of a single loop turns out to be K prime times 2 pi I A over A squared. There's the picture, there's derivation based on the force exerted by a small current segment. So we have to understand that. So point is, from this, whether we remember the details at the moment or not, we know we can calculate the magnetic field at the center of one of the loops. So we can get an order of magnitude for the current, or for the magnetic field. For I equals 0.4 amp, which is about what I think I remember we were getting through those coils, through a 6-volt battery. Yeah. We get the current of 0.4 amps. There's our I. Our total delta L is the circumference. Radius is 10 centimeters. Circumference is about 60 meters, 60 centimeters. So that B actually is equal to the sum of the delta B's. We went over this previously and explained why. Ordinarily, when you're setting up an integral, your total is not going to be equal to the sum. And the sum of your delta B's is about equal to this, but this is equal to this. Not going to worry about that. Let's just get a ballpark figure. We got and I didn't put my length in here. Like, I don't need the length because I divided it out here. We got the 2 pi. And it's supposed to be 2 pi. Okay, so what are the numbers? We got newtons per amp meter. We got a per meter down here that divides that. We got an amp that divides that. It's not newtons per amp meter, it's Tesla per amp meter. Okay, and we're going to get Tesla. What are our numbers? 10 to the negative 7th. We got 4 here, and 2 pi is about 24, 25. So unless I did something wrong, we got about 2.5 times 10 to the negative 6 Tesla. Okay, that's per loop. Now, that would be at the center of the loop. We displace by 10 centimeters out here. Then we get a slight change in this. It's probably down to about 1.5 times 10 to the negative 6 Tesla. Now we've got 100 loops. And we get about 2 times 10 to the negative 4th Tesla. we used a slightly different number of loops before, and we've got something that was about 3 × 10⁻⁴ Tesla, which is about 10 times the strength of the Earth's magnetic field. Okay, so we've got this magnetic field that suddenly turns on when we connect the power source. Now we've got this coil. It's kind of a solenoid, but kind of not a solenoid. It's not a tightly wound coil. So whatever this is, however we treat it, using Ampere's law and stuff. Excuse me. There's a bunch of turns in here. And let's just say there are 100 turns of radius 3 centimeters. Okay. When we turn the magnetic field on, that field penetrates each of these loops. Okay, each turn. So you have a flux of 100 times the number of turns. That's all, well, if there are 100 turns, 100 times the flux through one loop. Flux through one loop is magnetic field, which we just approximated, right? Multiplied by the area inside the loop. If the radius is 3 centimeters, then square would be 9 square centimeters. 3/4, that'd be about 7 square centimeters. So something like a coil or a solenoid. Can't really treat it as a solenoid because it's not quite long enough, and you get a lot of edge effect, but you'd still get a decent approximation. Or a tightly wound coil where all the loops are pretty much in the same plane. We don't have that either. So I just say it's kind of a coil solenoid. We're not going to be real accurate in approximating it, but we're not going to be that inaccurate either. So we insert a coil solenoid and we'll treat it as if it's just a coil. Okay. Now I said the area of that thing's actually 7 square centimeters or so. Let's use nice round numbers. We use 10 square centimeters just to make the numbers easy to deal with. Okay. So ten square centimeters is 0.001 square meter, which is 2 times 10 to the -7th Tesla meter squared. Flux through other terms is 100 times 2 times 10 to the -7th Tesla meter squared equals 2 times 10 to the -5th Tesla meter squared. Okay, well, those numbers are kind of handy. They might be accurate. I might have made some bonehead mistake. You get the idea that it's pretty easy to analyze this based on what we already know. The other thing is, we noticed a little deflection of the needle, but it deflected and it came back, right? It kind of did this. Okay? Now, for instruments work, we'd be able to get a readout of that. I'm keeping my fingers crossed that everything's working on Friday. The current in the large coil alternates. And the magnetic flux, which I'll call 5V, in the small coil, keeps changing. That makes sense? So like if I'm driving this thing with an alternating current, and 60 times a second, flux will change from positive to negative to positive, okay? Along a sine curve. In that case, use this for EMF. Usually use V for voltage produced by a battery or source of direct current. An EMF if we have a change in current. But there's no hard and fast firm rule for when we use which symbol. What we get is the field is negative d pi dt. That the field of the EMF is the rate at which flux changes. I'll write that as the rate of change of the flux. Now, let's just say, for example, this setup assume the current is I of t equals 50 amps times sine of 125 joules. Now, how does a sine of 120 pi t behave? Okay, now we've got an estimate. If we got 4/10 of an amp, we're estimating we have a flux of about 5 times 10 to the negative fifth Tesla meter squared. Okay. And we, without having to redo the calculations, which might or might not be completely right, can we use this information at 4/10 of an amp to figure out what the flux would be? Okay, so we didn't get a real quick answer here. We've got a couple of pretty quick attempts. Let's break it down. Basically, 4/10 of an amp gives us this. 50 amps is a lot more than 4/10 of an amp, right? Now, if we increase the number of amps, what does that do? We increase the number of amps, that increases the magnetic field, which increases the flux, right? So if we had 8/10 of an amp here, we'd have twice as much current, twice as much magnetic field. Okay, you know, we use the 4/10 of an amp to get this, okay? If we use a bigger number here, we're going to get a bigger number here. It's going to be just directly proportional to the number of amps that we have. So this is the field. We multiply that by the area, approximate area of a loop. And then we multiply that by the 100 loops. And we got this. Now again, we calculated this for one loop, for 100 loops, we got this, etc. So you can trace that down. The whole point is that phi of t would be okay. Now 0.4 into 2 is 5. 5 times 50 is 250. Got 2.5 times 10 to the negative fifth Tesla meter squared. But of course, then you got times the sine. Now I'm just carrying the sine along here. Writing it out in all its glory. Going to have amplitude 2.5 times 10 to the negative third Tesla meter squared times the sine of 120 pi t. Okay, so now what's d pi dt? The EMF is the negative of d pi dt, the negative rate of change of flux. Okay, well, this is a common and more or less trivial derivative, but let's just write it out. We're going to have negative 2.5 times 10 to the negative third Tesla meter squared times negative 120 pi cosine of 120 pi t. Maybe a little hard to read there, but I'll write out the final result. Well, I got a negative here and a negative here. 2.5 times 120 is 300. or can't get that cosine in there, but I think we know what we're looking at. Well, 300 pi is about 1,000. And since we're doing d phi dt, we get Tesla meters squared per second. They're actually dividing by a t when we do this. And we get approximately pretty close to 1 Tesla meter squared per second. Times cosine of 120 pi t. So we get an alternating voltage, which is going to give us an alternating current in this loop. Okay. And we could tap off that current. The loop, I think, has a, this thing, coil solenoid thing, this thing. I think it has a resistance around 10 ohms. I'm going to get about 1/10 of an amp of alternating current here. Okay, so if you have a picture of the Helmholtz coils and the magnetic field penetrating the Helmholtz coils, a more or less constant magnetic field, we can approximate that magnetic field. We can approximate it a little more closely by moving 10 centimeters perpendicular to the plane of each loop. We get the accurate number of loops. But we have a picture of the magnetic field penetrating the loop and creating a flux. If we have an alternating current, then the magnetic field keeps growing. Okay, grows in this direction, shrinks back to 0, grows in this direction, shrinks back to 0, grows in this direction, shrinks back to 0, grows in this direction, shrinks back to 0. Does that make sense? 120 times a second. Okay. Which means the flux in this thing changes at this rate. Now, what's a Tesla meter squared per second? That's a volt. That's 1 volt times the cosine of 120 pi t. Now, the second here comes from the fact that it's 120 pi hertz. Okay? So it's 120 pi hertz, and I probably should have left that in there because a hertz is a cycle per second. That's part of your constant here. So when you take the derivative, that's where the second out here comes. Okay? And from the chain rule, the derivative of 120 pi hertz is, the derivative of 120 pi hertz times cosine of 120 pi hertz times t is 120 pi hertz times all this. Now it's a little sloppy with my unit set. Understand what I mean? Okay, that the 120 pi has units of cycles per second or hertz or reciprocal seconds. So the reciprocal second comes out when you use the chain rule, and that's where the reciprocal second comes out here. So I can erase the hertz here. Put the reciprocal second here. Okay, well, that's alternating current. And the source of alternating current the source of the current, the 50 amps times the sine of 125 T comes from a coil rotating in a magnetic field. The coil rotates 60 times a second. Now, if the configuration is a little different than this, but what happens in the power station, whatever is driving the power station, be it steam from a nuclear generator or from a fossil fuel plant, okay, whatever, ultimately, you're probably driving a dynamo using steam from some power source. Drives it through the magnetic field and creates an EMF that gets distributed over power lines and so forth. Okay. So the 120 pi t just comes from the rate at which, the conventional rate at which the coil essentially rotates. All right. And we keep it at 120 pi because our devices are welded to the 120 pi. Are wedded to the 120 pi. What would be the difference now? And we got 1 volt here, okay? What would be the difference if the area of that small coil was equal to the area of the big coil? So let's say we have just a very slightly smaller set of Helmholtz coils inside of those coils. What would change in all these calculations, starting over here? What changes if our secondary coil, the one that was small, gets bigger? Okay, so point is now, if I increase the area of the coil, of that secondary coil, blow up this small coil solenoid, whatever it is, where it has the same cross-sectional area and the same number of turns as the original, as the Helmholtz coils. Well, by increasing the area, I'm going to get a lot more flux, right? So if I increase the area by a factor of 100, I'm going to get 100 times as much flux. Increase by 1,000, which I can do by doing a lot of terms, I get even more. Well, then if I put that inside of these coils, I can end up with a small voltage. If I got 100 times the area, I get 100 volts, okay? If I got 1,000 times the area, I could get 1,000 volts. It just comes down to the area and number of turns. So when you read about transformers, you see a formula for that idea, but that's the principle behind a transformer. Your book has better pictures than I can draw, and I don't know. I kind of go by what I could understand when I was in high school and fairly stupid, and I'm still fairly stupid, but not as stupid as I was. I didn't know much, okay? But it was easy to grasp transformers. People found it fairly easy to grasp transformers, at least the rules. Right there's the real reason for it all. And we didn't get that. So I'm going to assume that you're going to be able to figure out transformers. This is Faraday's law. Lenz's law is kind of a corollary but it's handy to know that when you, I mean, they're going to be really important, very short, okay? When you start increasing the field here, okay, so you increase the current. So let's say you throw the switch, you get the magnetic field from the coils, from the Helmholtz coil, penetrates here, creates a voltage around here, which will create a current. And that current is what we measured when we ran these leads through the galvanometer. We got a very tiny response, but we did get a response. Okay. Now, problem is, even if the magnetic field occurs instantaneously, which practical forces it kind of does, this thing doesn't build up its voltage instantaneously. Because as this thing builds up a current, it doesn't build up its current. I mean, it gets its voltage, it doesn't build up its current instantaneously. It can't. Because as it builds up the current, it creates its own magnetic field. Okay? Yeah, and you always say, you know, the loop creates a magnetic field within it. These loops create magnetic field in here, and that magnetic field opposes the increase. Okay? So that magnetic field creates an EMF in these coils that counters the tendency for the EMF induced by the Helmholtz coils to increase current. Okay? And that's going to be really important. We'll probably have the differential equation for that shortly. Okay, I'm probably almost done like that. First of all, induced EMF causes a current in what I'll call the coil solenoid. Current creates a magnetic field. And I'll just use the word coil because I don't want to write solenoid. Okay. Um, Magnetic field in the coil I'm saying there's a change in field. Excuse me. This change in field. Uses an EMF in said coil. Acts counter to the magnetic field. Counter to the EMF. Everybody will have those coils. You got the big coils, you got the little coil. Okay. Run a current through the big coil, the current's changing. Then your magnetic field's changing, which induces an EMF in the little coil, which causes a current in the little coil, which creates an EMF itself within the little coil that fights the EMF that's being created by the big field. If this current changed too quickly, the back EMF, okay, so we're going to say, and those coils create a magnetic field changing, it's oscillating back and forth, okay? Goes this way, goes back to zero, goes this way. Okay, so we have a changing magnetic field here. In any instant, that's going to tend to create a current here, but it can't build the current too quickly. Because if the current built with infinite speed, you would have an infinite rate of change of the flux in here due to the current in these wires themselves. Okay, if the current in these wires themselves changes too fast, you get an EMF that acts opposite to the EMF of the, okay, so magnetic field. Let's say the magnetic field is producing an EMF that tends to run the current counterclockwise. Okay. As that current increases, the counterclockwise current increases, it creates magnetic field in here, changing magnetic field that causes an EMF that tends to make current want to go this way. If that happened, okay, if the current created by the external field increased instantaneously, you'd have an infinite back EMF and nothing would change. And of course, you've got a superconductor, you know, you kind of get close to that. Okay. So that takes a little sorting out. I'll say the current in the coil can't change so fast self-induced EMF. Phase the EMF. Due to him on quote. Okay. Coil has an inductance L. Which when multiplied by di dt gives the back EMF. The back EMF is EMF that's self-induced in that coil. It tends to resist the increase in current. Okay. Simple circuit that we actually were observing. Coils of the galvanometer. This doesn't have to be a coil within a coil. Actually, I don't want to do an overnight source. I just want to consider what happens. You got just good old batteries. And a switch. There's some kind of a coil. So the resistor has existence R. Source has a voltage V. This thing has inductance L. Okay. Close the switch. What happens? Current starts flowing. Current starts to build. Not too fast. Why not too fast? Well, if you look at the voltage drops, voltage drop in your inductor depends on how fast the current changes. If your current is driven this way, then of course you have voltage drop, current times resistance. In the resistance, you have a voltage rise as you go through V, so there's a negative voltage drop. Why is there a voltage drop across L? It's because the rate of change of flux causes a voltage through L, an EMF through L. It causes the magnetic field to build in L in such a way that it resists the increase in the current. No more detailed picture, but right now let's accept that much. So this is differential equation, of course. It's a simple one. Actually, it's not that simple. You got I in here. But I don't want to do this. Not going to have zero resistance anyhow, unless you have a superconductor. We don't talk about that yet. Okay, now I'm beginning to talk about something that comes up later. Is in this chapter. Okay, so I'm going to try to stay on topic here. There's a circuit that we'll observe if we can find, if we get our instruments to work, where we can very clearly see the exponential growth of the current in a situation like this. We'll save that until we get there. Okay. Now, another way to get an EMF. Let's just say we have a bar with conducting bar. And there's a magnetic field. Okay. And let's just say the magnetic fields of an island. Out of the language. So this thing's moving at velocity v. And then the charges. You got a charge in here. Let's just say you've got positive charges, even though you know you got negative charges. You got positive charges. And those positive charges are moving this way in a magnetic field that's directed this way, giving you force in this direction. Okay, makes sense? Positive charges. The direction V cross B. Right. Negative charge. Go to the left. So you would end up with excess positive charge on this end, excess negative charge on this end, and an electric field. From positive toward negative. Electric field in the direction in which a positive charge would experience a force. Magnitude, the electric field that you get an electric field because again, positive charges are going to be moved in this direction because of B cross B. And negative charges in this direction. So you got an electric field, which is a kind of a script E. Here for it. Magnitude of that is VBL. It just comes from the PV cross L, okay? Or QV cross, sorry. IL cross B or QV cross B. Okay. Have this. If it's not a straight bar, then you have to integrate. B cross B, GL. We'll talk more about that next time. Try to get the flux picture. The whole thing about rate of change of flux is induced EMF, and then how a changing current in a coil creates a back EMF. Use your right hand and come in questions you have.